Okay, everybody, here you go. Here's your crash course in right triangle trigonometry. So, hi, Cleo. Cleo really wants to know about right triangle trigonometry. So, here's the thing. So, all of this has to do with right triangles. So, this entire chapter, which we'll be doing as soon as we get out of the chapter on transformations, has to do with right triangles. So the basis of a lot of what we're going to do is going to be found in the Pythagorean Theorem. So we have a squared plus b squared equals c squared. Once again, Cleo loves the Pythagorean Theorem. So this can be used to find any of the three sides, and that's how you do it. So c equals the square root of a squared plus b squared, a equals the square root of c squared minus b squared, and b equals the square root of c squared minus a squared. Okay, and that's simply a manipulation of that top thing there. Triangle is what it's called, equation. So you, like, to find a squared, you subtract b squared and then take the square root. So there are two special triangles we're going to be dealing with. And those are the 45-45-90 triangle and the 30-60-90 triangle. So we're going to start off with the 45-45-90 triangle. Now, what the 45-45-90 triangle is a half a square. So we took the diagonal of a square. And when we do that, we know that the diagonals of a rhombus bisect the opposite angles. We know that the square is a rhombus, so that we know that when we take the diagonal of the square, we get two 45-degree angles. Because it's a square, we know that the sides are the same length, and let's say that they're both 1. So using the Pythagorean theorem, how would we find for the hypotenuse? Well, we'd go 1 squared plus 1 squared equals c squared. That gives us 1 plus 1 equals c squared, or 2 equals c squared. We take the square root of both sides, and we get c equals the square root of 2. Now watch what happens when we do another 45-90 degree triangle, except this time, instead of using 1, we're going to use 4. Okay, so now to find that diagonal, come here. Come on, Mama. We're going to go 4 squared plus 4 squared equals c squared. Hey, your baby girl. So that's 16 plus 16 equals c squared, or 32 equals c squared. Now when we take the square root of 32, that's the square root of 16 times the square root of 2, or 4 radical 2. Okay? What's up, Cleo? Cleo doesn't like Rama being on the couch. So, what that does give us is that the ratio of the side in a 45-45-90 degree triangle are always in the ratio of 1 to 1 to the square root of 2. That means that the hypotenuse, that's too far. Don't look. The hypotenuse of the leg is always square root of 2 times the hypotenuse of the leg. That's not a thing. The hypotenuse of the right triangle is square root of 2 times the leg. Now notice I call it an isosceles right triangle, and it is. It's an isosceles right triangle because we know both of the sides are the same length. So 6 and 6, and then we just go 6 square root of 2. Well, what if we were given the hypotenuse and we were asked to find the legs? And this is, again, in actual class, we'll go over this much, much slower. But if we go 4, okay, we know that our base ratio, or our basic ratio, is 1, 1, radical 2. We then are going to have a scale factor, which goes all the way across. And that's going to leave us with the actual length. Now here, we know that that base ratio of 1 square root of 2 is the 1's are the legs and the square root of 2 is the hypotenuse. So we go, okay, well, and the scale factor, just so you know, has to be consistent throughout. So we go, what times the square root of 2 equals 4? So we divide the square root of 2 by both sides. Divide both sides by the square root of 2. And we get 4 over radical 2. Well, we can't have that, so we're going to need to rationalize our denominator. We've done this. So we're going to multiply it by the square root of 2 over the square root of 2, or 4 radical 2 over 2, and that's going to give us 2 radical 2. Okay? So that's our scale factor, and then that also becomes the actual length, because we're just multiplying it by 1. Now, our second special triangle is the 30, 60, 90 triangle. And we get this by cutting an isosceles triangle in half. Now notice when we bring down that altitude, it's 90 degrees. That corner there is already 60 degrees because it's an isosceles triangle. And that leaves us with the angle we split up top as 30 degrees. Now the ratio of sides here is always going to be 1 radical 3, 2. Okay? Now keep in mind that the 1 ratio is always across from the 30 degree angle. The square root of 3 is always across from the 60 degree angle, and the 2 is always across from the 90 degree angle, or the hypotenuse. Now a lot of people refer to this as a 1, 2 square root of 3 triangle, which is true, but I think that a lot of people then get confused and end up putting the square root of 3 on the hypotenuse. And this is important. The square root of 2 is equal to the square root of 4. That's not the square root of 2 is equal to the square root of 4. 2 is equal to the square root of 4. So if 2 is equal to the square root of 4, then we can see that the square root of 4 is bigger than the square root of 3. A lot of people look at 2 and the square root of 3 and go, oh, the square root of 3 is bigger, so they put that in the hypotenuse. And that's a bad idea because it's wrong. So here, if we have a 4 right there and it's across from the 60, and we're trying to find our x and our y. And I'm probably going to make a lot of mistakes talking on this. I don't know if you guys can see the time, but it's 12:30 in the morning on Wednesday. So I apologize for how late this is, and so for probably how stupid I sound, and for how often I'll be talking to my animals. Hi, Rama. Hi, Rama. She thinks I'm stupid, too. Well, not stupid. She just thinks I'm being stupid right now because she wants to be sleeping. So our basic ratio is 1 radical 3, 2. We don't know what our scale factor is. And so for our actual sides, we need to figure out where to put the x, the y, and the 4. So we know that that's our 30, that's our 90. Now remember what I said. The 1 is always across from the 30. So that means that the x is going to go there. The 4 is going to go across from the radical 3. And the 2, or the y, is going to go across from the 90 degrees. So that's in our 2 slot. So notice what we have here. We know that the square root of 3 times our scale factor is going to equal 4. So we're going to divide both sides by the square root of 3. And we get our scale factor as equal to 4 over radical 3. Again, radical 3 is not a rational number, so we need to rationalize our denominator by multiplying it by the square root of 3 over the square root of 3. That gives us 4 radical 3 over 3. So that means that our scale factor is 4 radical 3 all the way down. That means that x is equal to 4 radical 3 and y is equal to 8 radical 3. Easy peasy. Over 3. over 3 over 3. So here again, if I know that it's a 30, 60, 90 triangle, it is in the ratio, those sides are in the ratio of 1 square root of 3 to 2. Now keep in mind that this comes from similarity. So all 30, 60, 90 triangles are going to be similar to all other 30, 60, 90 triangles through angle-angle similarity, which means all of their sides have to be proportionate. That's the definition of proportionate. So we know that these proportions have to be the same. So if the 30 is across from the 3, then we know that's the 1. We know that x is going to be our square root of 3, and y is going to be our 2. So we go, what times 1 equals 3? Well, that's easy, it's 3. So we know that x equals 3 radical 3, and y equals 6. So now we're getting into what are called trigonometric functions. And they tend to scare the crap out of people, but they're actually really simple, and they rely heavily on your calculator, which is great because that means you don't have to actually know how to do the math. You just need to set up the problem. So here I have 3 30, 60, 90 triangles. Okay, so 1 radical 3, 2, 4, 4 radical 3, 8, and 6, 6 radical 3, 12. Now notice that the ratio of the short leg to the hypotenuse in all of them is 1/2, which we'd expect because of similarity. So this is just an application of the triangle similarity that we've already done. So I'm going to start off by saying the constant ratio of the side opposite to the 30-degree angle in a right triangle to the hypotenuse is 1 to 2, or 1/2. And I hope that everyone would agree with me on that. That's what we just did. But that's a lot to write. So instead, what I'm going to write is that the sine of 30 equals 1/2. And that's all that sine, cosine, and tangent are. They're an expression of the ratios. So these are your 3 trigonometric functions. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is adjacent, opposite over adjacent. So, if we have our basic 30, 60, 90 triangle, now keep in mind, these sine, cosine, tangent things work for any right triangle, okay? It doesn't have to be a 45, 45, 90. It doesn't have to be a 30, 60, 90. If there is a right triangle there, we can use it. So, if I were to say, what is the sine of 30? Well, it's opposite over the hypotenuse. What's opposite of 30? 1. What's the hypotenuse? 2. If you hit 30 sine on your calculator, you'll get a 0.5, or sine 30, depending on how your calculator works. Cosine of 30, square root of 3 over 2. That's the adjacent. So opposite is there, adjacent is next to. Tangent of 30, that's opposite over adjacent, which is 1 over the square root of 3. And I'll multiply both sides by the square root of 3 over 3, which gives me the square root of 3 over 3. When I said square root of 3 over 3, I was jumping the gun. We're actually multiplying it by the square root of 3 times over the square root of 3. The sine of 60. So here for 60, notice that that square root of 3 is opposite. So we get the square root of 3 over 2 is the sine of 60. The cosine of 60 is 1/2. And the tangent of 60 is the square root of 3 over 1, or the square root of 3. For a 45, 45, 90 triangle, it breaks down like that. The sine is square root of 2 over 2. The cosine is square root of 2 over 2, which makes sense because the two legs are the same. So the opposite leg and the adjacent leg are going to be the same. And the tangent of 45 is 1. Now, it's an A. A way to remember this is so-ka-toa. It sounds like some Hawaiian dance chant. So-ka-toa, so-ka-toa. But all it stands for is sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over the hypotenuse. And the tangent is equal to the opposite over the adjacent. So if you forget which is which, remember so-ka-toa, and that will help you remember kind of what sine is. So, S-O-H, sine is opposite over hypotenuse. Okay, so here we have a triangle, 8 by 15 by 17. I'm not sure whether that actually works, but we're going to pretend it does. And we have our x and y degrees. So if I wanted to say what is the sine of x, I'd go opposite, 15 over 17. Cosine of x, 8 over 17, because that's the opposite, that's the adjacent. Tangent of x is 15 over 8. Do it for y, and those would be my answers. Because remember, the sine of y and the sine of x are going to be different because we're looking at it from a different position. From the x position, 15 is opposite. From the y's position, the 15 is adjacent. Okay, so when we're talking about sine, cosine, tangent, it's important to reference where we are. Okay, so it just can't, what's the sine of that triangle? That doesn't work. But if we sit there and say, what's the sine of x? They're like, okay, our perspective is from x's perspective. What's opposite of that? And that would be the 15 side. Okay? And this is how we use it. So let's say I have a right triangle with a 45 or 54 degree angle, and the hypotenuse is 18. And I want to know what one of the legs is. Well, I look at that and go, okay, I know that I have a 54 degree angle, and I know that the W is opposite that 54 degree angle. And I also know that the hypotenuse is 18. So what I'm going to do is I'm going to go the sine of 54 equals W over 18. Hey, Cleo. Say hi to everybody, Cleo. To like both of the people who are going to watch this, Cleo says hi. We then multiply both sides by 18. We get 18 sine 54 equals W. Plug that into a calculator and we get W equals 14.56. Now this is how you plug it into a calculator. And it differs. Some calculators, the ones that you use in class, you're going to go 18 times the sine of 54, and those are the buttons you do, and you hit enter. However, if, like on my phone, you have a scientific calculator, sometimes you need to hit the sine second. So you hit 54 sine, and then as soon as you hit that sine button, it's going to calculate the sine of 54. So you end up with a really complex number, and then you multiply that by 18. And if you're doing it right, you should get 14.56. If I were you, what I'd do is I'd play with the calculator you're going to use on the test for a little bit. Make sure that you can get 14.56 as your answer to this problem. Here we have 28. We have the opposite side as a 1. The adjacent side is the W. So that would be tangent. So when you have a problem like this, what you want to do is identify which trigonometric ratio we're using. So we know that the tangent of 28 equals 1 over W. So we're going to multiply both sides by W. And we get W times the tangent of 28 equals 1. If we divide both sides by the tangent of 28, we get W equals 1 over the tangent of 28. Plug that into my calculator. I get 1.88. And depending on what kind of calculator you have, that's either going to be plugging in, either going to be 1 divided by tangent 28, enter, or 1 divided by 28 tangent, enter. Again, get to know your calculator, figure out which of these you're going to be using. Okay, now I want to talk about inverse functions. So just like we can use a side and a angle to find the other side of a right triangle, we can actually use the sides of a right triangle to find the angles, and here's how. So let's say we have your basic 3, 4, 5 Pythagorean triplet here. And I want to know what that angle right there is. This is what I do. I'd start off by saying that the sine of my missing angle is equal to 3 over 5. Right? Because that's opposite is the 3 and the adjacent, and the hypotenuse is the 5. So the sine of x equals 0.6. Well, that's great, but how does that help us? Well, on your calculator, very frequently, directly above the sine button, is another button that states sine to the negative 1. Okay, it's not a button, it's really just listed there. So you want to hit your shift button or your second button or something like that. On the ones in the classroom, just hit the button with a color, either blue or green, that tracks with what you're trying to do. So we take the inverse sine of both sides, and we get x equals the inverse sine of 0.6, or x equals 36.9. So what I want to do now is show you, so I'm either going to hit second sine, 0.6, enter, or I'm going to hit 0.6, shift, sine, and that'll give me the inverse sine of 0.6. Notice we could have easily used tangent or cosine. Stay. There's a cat outside. Mama, knock it off. What? There's now a cat inside. Rama, knock it off. Leave Thespis alone. Thespis, stop going outside. Okay, now that we've gotten that. So the tangent of that would be 0.75, 3 over 4. The cosine would be 4 over 5, because that's adjacent over hypotenuse, or 0.8. And if I hit the inverse tangent of 0.75 or the inverse cosine of 0.8, I'd get 36.9. So it doesn't matter how I approach it, any of those will end up with the same thing. So angle of elevation, this is the last thing we're going to be doing, angle of elevation and angle of depression. Okay? The angle of elevation is what happens when you're looking up at something. Okay? So if I'm on the ground, I look up and I see a plane, the angle of elevation is the angle between the plane and myself. The angle of depression would be from the plane back down to me. So if it is opening upwards, if it is, so what you do is, a lot of these have to do with line of sight problems, or like a bird in flight or something like that. And so if it is above kind of that horizon line, that flat line straight in front of you, then it is an angle of elevation. If it is, Rama, get out. Rama, come here. Rama, leave it. Come here. If it is like looking down from something, like you're at a, So if you're on the ground looking up, angle of elevation. If you're at a high place looking down, angle of depression. And here's how those are used. So let's say 6-foot dude standing there 1,000 feet away from the cliff. It's Andy. Andy decided to go back to cliff climbing. He saw the something solo documentary, and he wants to climb cliffs. So he's standing 1,000 feet away from a cliff face, and he measures the angle of elevation at 34 degrees. He now has, without shadows or any other measurements or triangles or, because we already did the indirect measurement thing, he now has enough information to find out the cliff height. So he knows that the cliff height, which it's called x, so he knows that the tangent of 34 is going to be equal to x over 1,000. Multiply both sides by 1,000, we get 1,000 times the tangent of 34 equals x. Plug that into a calculator, and we get x equals 674.5. But we need to add 6. Why do we need to add 6? Is because the dude, Andy, is sitting there looking up, and his eye line, the kind of the 0 degrees that we're taking from or for the angle of elevation, his eye line is 6 feet off the ground. So if we want to know the total height of the cliff, we need to take this x portion, nope, wrong button, this x portion right here, and then add the 6 feet that are right there. And that'll give us the total height of the cliff. So, now Andy is out flying a rescue plane, and he's flying at a consistent 3 kilometers off the ground. He notices the life raft at a 24-degree angle of depression, and so he tries to find roughly where on a map that's going to be. So he needs to know how far out in front of him it's going to be. So what we're going to do is we know that it's 3 kilometers high. So we know that the tangent of 24 equals 3 over x. Math that around a little bit, and we get x equals 3 over the tangent of 24. Plug that into our calculator, and we get 6.7. Okay, again, this is not meant to replace everything we're going to learn about trigonometry, but hopefully it'll give you guys a legit shot at least maybe guessing the right answer on any problem with right-angle trigonometry. So that was, chapter 6 in half an hour, or whatever chapter that was, 7 maybe, I don't know. Good night, everybody.